Yeah, so those who have joined can just enjoy seeing this uh, funny anecdotes in the history of NLP. Like the left one is a case when the I don't remember who, but somewhere in the 1950s, people made this translator using some hard-coded rules and all to translate from English to Russian. So, and back from Russian to English. So they tried this sentence: "The spirit is willing, but the flesh is weak." And it got converted to Russian. And on converting that Russian sentence back to English, they got the vodka is good, but the meat is rotten. So, like, it just shows that hard-coded rules are not what we want. We actually want understanding, a deep understanding of the meaning. Similarly, there was a case where out of sight, out of mind was translated as invisible and insane. So yeah, just a few funny things to show that the field is both interesting as well as difficult. Yeah, and this is the world's first chatbot developed in 1966 by Joseph Wiesenbaum. And yeah, it was made as a psychotherapist, mock psychotherapist, which will ask you questions. It will give you some hard coded answers based on some parts of your response. And yeah, if in today's date we try this, it will give us very, like, we can easily find phrases, prompts to uh, just fool this chatbot. So yeah, I think it's 7:41, so I'll start. Yeah, so okay, starting with what is NLP? NLP is the journey from the ideas presented in this paper to finally wait. If you this is a paper written in 2011, like just 14 years ago. Natural language processing almost from scratch, and the introduction itself says that will a computer program ever be able to convert a piece of English text into a data structure that describes the meaning of the natural language text? Unfortunately, no such consensus has emerged, and until such problems are resolved, we have to settle for only reduced objectives, and we cannot do much. And in fact, in the paper also, they do just some part of speech tagging tasks, like things like I have a sentence, just tag out all the nouns, all the verbs, and things like that. So in even in 2011, they were believing it is quite impossible for the program to understand a language. But yeah, just some 14 years later, we have this chat GPT. You just tell it anything, it will, like, it can do everything. So basically, how is this possible? So let's start with this. Domains that come under NLP are like, there are many, but like strictly categorizing them or strictly taking only the main ones. The first thing that comes to mind is text generation. All the language models do this. How text generation works, I'll just introduce in brief, because mainly it was covered in the attention is all you need sessions by Samruddh. But yeah, text generation is basically auto regressive. So you have uh, a seed of text or a array of text. You feed the model that text, and the model will predict the next word, and so on. We will do this process again and again to generate a piece of text. Okay, fine. Then machine translation, translating from one language to another. Retrieval mechanism is basically what these search engines like Google and all use to see. They have millions of documents available across the web. So what they want to do is they want to retrieve the only the most relevant ones to the query. So how to find which document is more relevant? That is one thing. Another thing is text classification. I want to classify a mail as spam or not. Question answering, like say people want a question answering website chatbot on their website that answers questions related to their company. Next is auto correction or completion, which we knowingly or unknowingly use on whenever we use keyboards on mobile. So yeah. And semantic analysis is basically a kind of text classification only, where we want to classify the sentence as written in a happy mood or a sad mood, or like find the mood of the sentence based on the uh, uh, based on just the sentence. I don't have anything else. So yeah, these are the main domains under NLP. We will touch few of them one by one. There are many others also, but yeah. So starting with n-grams. Okay, so if you were there for the transformers session, transformers are like very advanced things. These n-grams are like just basic things, some basic things that statisticians tried earlier. So yeah, I'll start with this. Which of the following sentences look more meaningful to you? Like, I know both are meaningless, but yeah, can some of you unmute and just say which looks more meaningful and why?
I think the second one is better than the first one.
Yeah, but why?
Because again, it's describing the land as barren and, well,
But
phone
yeah, what
call
is phone
away.
call away?
Yeah, well, not sure.
Okay, yeah. So yeah, that's right. That's because we mainly see that there are a few group of words. Phone call away, away in the land is barren. These words look like meaningful. So a few group of words which we see very often are like more convincing than just some random words. Like demon like phone, what's that's nonsense. So that is the motivation behind n-grams. So what we assume is if a sequence of n words is occurring frequently, it is more meaningful. And if we are building a language model which predicts the next word given the previous words, this concept can help it. Like suppose if I have phone call, it will make more sense to predict away because phone call away occurs very frequently in my training data. So something like that. So let's go with the definition of n-grams. So n-gram is a contiguous sequence of n words from a given sample of text. Suppose this is my text. They can be used for the variety. If I am extracting unigrams means like just a single words. They can be used. All these will be called the unigrams. Bigram mean two word sequences like they can be used, used for, like all these. Similarly, trigrams, fourgrams, and all I can use these like I can capture and store all the n-grams present in a data. So what data? I'll take a corpus of text. Okay, first I'll explain how this can be used in text generation. Like it is a very simple concept. Actually, it's a concept of English grammar rather than AI. But yeah, so from a corpus of text, I'll extract all the n-grams. N is a hyperparameter I can control. So basically, if I have a okay, what is a corpus? Is basically corpus is a like a huge storage of data. Like I have lots of data, lots of text data, and I'll extract all the n-grams and store their frequencies. Like suppose this is I choose n is equal to 2, so bigrams. So I'll store all these things from a corpus, corpus of, and things like that. I'll store and I'll store their frequencies, like how often of the this diagram appears in the text. I'll show this. Now, when I want to do a text generation, I'll need a seed. So I'll take a seed of n minus one words, and iteratively I'll choose the next word from these n-gram model. Like from this n-grams, I'll choose the n-gram which is the most frequent. Like suppose I am storing trigrams. Now I have a seed as once upon. Now, once upon, if I have trigrams stored previously, I'll find that many trigrams are possible. Once upon, when, once upon, in. I'll just see which of the trigram is most frequent and I'll choose it. I'll choose that word. So I got another word. Now I'll choose the last n minus one words again and again, and I'll just go on. Now this sampling can be done in a greedy manner also. Like I'll just see that once upon a is more common than other. So I'll choose once upon a. Or I can take a random manner, like I can weight their frequencies and like choose one. So things like that. So here is I'll show you how it is implemented over here. So yeah, in this notebook, Okay, I don't use any other library, but just this Hugging Face data sets to have my training data. I use Wikitext. It has like a lot of Wikipedia data. This is just an example. So yeah, and one thing is it has masked rare words by this unknown token, because rare words are mostly a hassle even in transformers. So we mostly mask them by this unknown token. Like there is some unknown word, forget it for now. So yeah, and yeah, these are the functions to pre-process to build n-gram models. I build only till 6-gram models. We can make more also, but yeah, I'll tell you 6-gram is also very bad, like not useful at all. And I write the function to generate text. Okay, so yeah, I pre-process my corpus and build this bigram, trigram, 4-gram, 5-gram, and 6-gram models. And yeah, just for the sanity check, like this can show you how it is stored. I am storing this is the list of trigrams. So trigrams I'm storing as this, like say of the, after of the 605 times there is an unknown token. 209 times there is a season token. 203 times there is a year token. So yeah, this is the just like this is the trigram of the unknown has a trigram is a trigram with frequency 605 and so on. Now I try this completion. I give these as the seeds. For the bigram model, I need only one word as a seed. I give by. For trigram, I give by the and so on. And this is what is the completion. Like yeah, as we go below, it becomes more and more meaningful. I can explain you. First word was by. The model saw that after by the most frequent word is the, so it predicted the. After the most frequent word was unknown, and after unknown, the most frequent word was again unknown. So it just fell into a loop. In the trigram model, also in the greedy completion, it fell into a loop. So yeah, after this, these sentences look a bit more meaningful as predicted by the 5-gram and 4-gram models. And yeah, so that is how this n-gram models worked. Wait, are you able to see my screen?
What's the difference between greedy and random completion?
Yeah, in greedy completion, I'm just selecting the most frequent word. In random completion, I am just selecting any of the next password. I don't know what's happening. Yeah, fine. This was for the text generation part. Yeah, any more doubts? Like, was I clear about this random completion?
Yeah.
Yeah. Okay. Yeah. So the next application of n-grams is wait. The next application is retrieval mechanisms. Wait, I think it's lagging. I'll explain till then. Okay, so for document retrieval, what we do is we have a bunch of documents, say hundreds of documents, regarding different things. So what I'll do is I'll store the n-gram frequencies of all the documents separately. So I kind of have an idea what these documents have more frequent. And then if I have a query, like suppose I have many documents, now I have a query, um, say what is n-gram or something. I'll take that query string and also break that query string into n-grams. And I'll check the frequencies of these n-grams in each of the documents. And I'll get kind of a score for each of the documents. Like some document might have more similarity with that query, so its n-grams might be matching more. Matching means like the same n-gram exists in the documents or not. So yeah, for the story example, I just took blogs from the AI Club's website. This one is zero to Mamba, like regarding the Mamba architecture. Then there is one about Minecraft, like using Minecraft for using AI for Minecraft, and the next one is Microsoft's Graph Rack. So yeah, I kind of know what the topics are in each of these. And yeah, I just wrote a function to build a triagram, and this is a function to retrieve things. So yeah, I'm not going much deeper. You can just see. I gave this query. These are some of the examples that use different track conditions. Like that's just a random sentence, but yeah, it gives each of the, like, it got a score for each of the document. Just a second. So it just normalized them to get these probabilities 50%, 33%, and 16%. Unfortunately, actually, since I'm talking about RAG, it should give me more to document 3 because document 3 was about graph RAG. But yeah, since there are other words in the other bigrams and other trigrams in the sequence, it is giving more preference to the first document, which might be having the same trigrams again. So yeah. So this is one of the shortcomings that, like, there are many shortcomings. This is not actually how we want the model to think of it. The model should actually extract the meaning of the document itself. But yeah, this is an initial try to make this work. Yeah, the next my screen is lagging again. Yeah, the next place where n-grams are useful is machine translation. So machine translation, they are not useful directly but indirectly. Suppose I have a model which can translate from one language to another, but it will give several sentences. Like suppose it is my slide visible. Hello. Is my screen visible?
It's white.
Yeah. Okay. Wait. Yeah. Um. Yeah, okay. Till the time it loads, I'll just explain orally. So yeah, there are suppose I have a model already which can translate from one language to another. I gave it the sentence I am going home, and yeah, it translated in Hindi as मैं घर जा रहा हूँ and मैं जा रहा घर हूँ. Like it gave two possible translations. The model is kind of stuck between two of these. Now I can, if I have the trigram frequencies of some large Hindi corpus already, I can just see that ghar ja raha has a higher frequency than ja raha ghar. So I can say, okay, the first one is a better translation and it will be more preferred. So yeah, this I haven't coded it out because like I don't have a model which translates and gives two possible combinations. Okay, next interesting application of n-grams is spelling corrections. So yeah, and this works very well actually. So what I'll do is I'll break each word into character trigrams. Character trigrams are basically, but I can take any n-grams, but yeah, trigrams work the best. So I'll just take a word and break it down into character trigrams, like 3 characters per chunk. And for any misspelled word also, like I'll do this for the entire dictionary of words. And similarly, I'll do for any misspelled word also. I'll just break it into trigrams. So for example, here I have misspelled the word environment. Got these trigrams where these 4 trigrams will be different from the previous. Now, see, I have these two sets. This is a set of trigrams. This is also a set of trigrams. Now, there is a similarity metric called Jacquard similarity metric to find the similarity between two sets. So it is defined as the size, the number of elements in the intersection divided by the number of elements in the union of two sets. So like, yeah, basically you can see if two sets are exactly similar, the intersection will be equal to union, and this similarity will be 1. If they are entirely disjoint, this will be 0. So yeah, this is a pretty good similarity metric. And now I can use this metric to find the similarity of this misspelled trigrams with every single word in the dictionary. So I'll show you its implementation. Uh, yeah. So yeah, I just wrote a function to generate the character engrams of words to find the Jacquard similarity, intersects length of intersection divided by length of union. And this is my spelling checker, which takes input as a dictionary. It will generate these engrams and store it. And when I want to check it, it will check the engrams and return the top 5 similar words. So yeah, suppose I gave it environment. Okay, yeah, in that example itself, like if you see the Jacquard similarity of these two words and the environment with correct spelling or the wrong spelling, it can be see, the intersection is the number of common words, which is 7, and the union of words is the number of unique trigrams in the union of these, so that is 15. So 7 by 15, it should give 0.467, and the similarity with all other words should be less than this 0.467. So yeah, here we can see that that is the case. The best suggestion is environment, the correct word, with similarity 0.47. For all other words, it's less than that. So yeah. Then similarly, after that, I've tried for this suggestion with 3 Gs, and it suggests me the correct word. And similarly, for if I give it a correct word already, like school, it will suggest me the correct word school with similarity 1. So yeah, that was about engrams. Yeah, so obviously engrams have many disadvantages. For one thing, wait, my screen is lagging again. Yeah, like can somebody think of a disadvantage with using engrams? Yeah, just unmute and answer.
Sure.
Hello, am I audible?
Yeah, yeah.
Yeah, yeah, like there are many disadvantages. Like some of them are obvious. Once you have heard about transformers, you know how the complicated math that goes into them. They are such accuracy. It is easy to find flaws in this reasoning.
No semantic understanding.
Yeah, correct. So that's the main thing. There is no understanding. We are just hoping that the n-grams capture the similarity. And apart from that, also the the main thing is data is passed. Like I first have to store a lot of memory. I have to store the frequency of each and every n-gram. And if as I increase the n, the it becomes more and more complex. Like what is the probability of having a word like once upon a time there lived? Okay, like this is still frequent, but say there are some unfrequent engrams, they will have very less frequency, and again there will be like unless we have a very large data set, a very large corpus having all the words ever written, then still it might work well, but yeah, that's not how it works. And there is no semantic understanding, as you said. There is context blindness. Like if I use it for text generation, After generating the 10th word, it has no idea what was the first word. So you can never expect it to write good sentences at all. And there is a fixed window size again, and you can't change it. And there is no way to train it also. Like in transformers, at least we have, like, if it's not working, we'll train it on one more epoch or something. Yeah, there is no way. Like, this is what we have. You can't improve it further. It doesn't understand grammar. And yeah, the main thing is you can't actually depend you can't improve it more. So yeah, so this was about engrams. Any doubts in engrams? Yeah, then okay, I'll continue with the next topic, which is unrelated with engrams, but yeah, again, a statistical technique used for mainly introduced for document retrieval. So yeah, as we saw, engrams are not an efficient way to see, because first of all, they don't understand the document. So next we thought, okay, for at least document retrieval, what we can do is we can have something called a term frequency. Like, a document has many terms. Many, okay, terms for now we can consider as words only. So a document has many words. Say I had those three documents: one about Mamba, one about this Minecraft, one about this graph rag. So I can think of it as a term frequency. If some term is used very much in a document, that document is mainly about that term. I can think of it that way. So I can introduce something called a term frequency. Term frequency is basically the number of the fraction of terms in the document which are that a particular term. Like, suppose I am searching among 100 documents for the document which contains information about computers. I'll just search for the. I'll just see which of the document contains the most fraction of its words as computers. So yeah, that is what is a term frequency. And just a second. So yeah, term frequency of a term T in a document D can be written as the fraction number of times the term T appears in the documents upon the total number of terms in the documents. So yeah, like it is an intuitive guess, but this metric is not so good. Why? I'll show you. So I'll just show you my code for this. Yeah.
By the way,
Okay. So
that
again,
number of terms in the document, is it like all the terms or just like, I mean, all distinct terms or just like full count?
no, all the distinct number of distinct terms.
Fine, fine. I
Yeah,
got
huh. So it's not necessarily a fraction. It can be a positive as well. Like, it can be greater than one as well. It's just the number of times a term T appears divided by the total number of terms in the document. Okay, so yeah,
fine,
again
got it.
for this, sorry.
No, go
Yeah,
ahead.
okay. So again for this, I'm using the same documents, same three documents. Uh, yeah, and I what I'm doing is I'm generating a matrix having the term frequencies of all the words in these three documents. So yeah, so this you can see ability, able, like all these are the words, and these are the frequencies of them in the doc. Yeah. So as you can see, some words like and you'll see later the. These words have very high frequencies. All other words have like low frequencies or maybe even negligible. So yeah, this is frequency distribution. So as you can see, the frequencies of many words is very less. For some words, it suddenly yeah. And what is this word, you might ask? It is nothing but the. Like the highest term frequency score in each document is by the, because the is the most frequent word occurring in all these three documents. So, but this is not what we want. We actually want the most important term to be reflected over here. Like for document one, it should show Mamba. For document two, it should show Minecraft. For document three, it should show graph rag or rag something. There is not what I wanted. So that's why what we want is actually we want to scale these words, the scores of these terms by a metric such that their scores become normalized. So what I actually want is there, right? Yeah. So in that matrix, what I want to do is I want each word, if you see. So yeah, I want to scale each of these rows by a term such that the rare words are scaled up and the common words like and the are scaled down. Like is not an important word in any of these any of these documents. It actually should become zero. So that's what I want. So that's how we introduce these the term called IDF, which is the inverse document frequency. So what I want is the rare words should be given more importance and the common words should be given less importance. So I want to scale each of these row. So what I'm doing is yeah. So yeah, so we want a measure of rarity of a word. So a measure of a rarity is the document frequency. Like if there is a word which appears only in one of the document, then it is rare and it should be given more importance. But if a word is appearing in all the documents, then it is a common word and we should not give it any importance at all. Like it should be zero actually. So we take the document frequency of the word. Document frequency is the number of documents where the word is where the term is occurring divided by the number of documents in my corpus. And this is the measure of a rarity of a word. Now, if I inverse it and multiply it with my term frequency, I should get a pretty good metric for my score. Like each term is each row of my frequency matrix is multiplied by a term which uh, scales the rare words higher and the common words lower. I don't know why it's not loading.
Akshay, would you like me to share?
Yeah, yeah, Sharan, you share and that
Yeah,
would be
sure.
better. I don't know. It was working earlier. I think because I this Teams is also on, it is lagging a lot.
Yeah, give me a minute.
Yeah.
Can you guys see? Guys.
Yeah, it's
Yeah,
visible.
it's visible. Yeah, yeah, it's visible for me too. Yeah, so we what we want to do is okay, can you go next? Yeah. So I'll multiply my each row, each term, sorry, each term column with this metric, total number of documents in corpus divided by the number of documents containing the term. So if a term is occurring only in one document, then the score will be multiplied by the total number of documents. So it will be its score will be magnified. And if a term is occurring in all documents, it will be just multiplied by one. So nothing will be happening. So this seems like a good metric unless until Shan, can you go next? Yeah. So the actual formula has a log. So now why this log? Like why do we want a log to this term? So this log is to dampen the effect of this fraction. Say this fraction is going okay, so this is an example which I give over here. Suppose there are a million documents and there is a term which occurs in two documents and another term which occurs in four documents. So if we just take this fraction is going to be double for one of the term and a double of the first term. So I don't want that. Like in a million documents, it does not matter if a term occurs twice or even 100 times. It should be equally scored, like nearly equally scored. So this log actually dampens that effect. And yeah, so also the terms that appear very often are since we are taking log of 1 is 0. So the terms that are there are directly take converted to 0. So yeah, I'll share this code later. Yeah, so final formula for the TF-IDF is this: the number of times a term T appears in documents upon total number of terms multiplied by the log of inverse of document frequency, which is total number of documents divided by number of documents containing the term T. And yeah, there is a byproduct of this technique. By byproduct, I mean there is something which was not expected, but yeah, that is kind of a useful thing. We'll come to that later. So yeah, Sharon, can you go next? Yeah, but again, this method also has many disadvantages. First is again, this ignores word order. All of ngrams and TF-IDF, all these consider documents as a bag of words. By bag of words, I mean their order does not matter. They just occur as things occur in a bag. So they don't have an order, and there is no context. There is no semantic or like synonyms are also not captured, and it is sensitive to noise, rare words. There is a high dimensionality again because my matrix is of dimensions vocabulary by number of documents. So that's a pretty huge dimension actually for the web where there are millions of documents. Then there are it assumes terms are independent, but that's not actually terms. The meaning of term depends on the context. And yeah, if there are very short texts, like say suppose I say a sentence is a document, then it is not very effective. Yeah, Sharon, can you go next? Yeah, okay. So till TF-IDF, does anybody have a doubt? Okay, fine. Yeah, next is Okapi BM25. Again, just it's BM means best matching. Okapi is the name of company which developed it, and 25 is the version number. And it is just a slightly modified version of TF-IDF, which tries to mitigate some of the shortcomings of TF-IDF. So one thing is, in TF-IDF, you never see the length of document. Say, like, if just to fool the system, I can make a document which has some content written in it, and after that, it has all the words of the vocabulary written one by one. So all the words will be present. Again, all the document frequencies will be changed. All the term frequencies will get changed, and the matrix, like, I can get an unfair advantage at a score. So for that, this is a method which also takes into account the length of the document. By length of the document, I mean the total number of terms, like the total number of words in the document, so that longer documents are not biased. And another thing is frequency saturations. Like it, just like we saw, log was actually trying to reduce the effect. Actually, even in TF-IDF, instead of log, we could have taken any concave function. We actually, what we want is, it should be an increasing function for sure, but it should diminish the results as we go higher. Like for the higher frequencies, the smoothing should happen, and that was what log was doing over there. So here also they are using log, but they are slightly changing it. So yeah, can you show the formula, Shadan? Next. Yeah, so this is the actual mathematical formulation. Okay, it might look unfamiliar, but yeah, when it says score of D comma Q and there is a summation, what summation means is, I suppose, actually I'm not going to search for terms, I'm going to search for the query. So that query might have many terms in it, like what is the capital, like whatever. It will have different terms, what is the, and so on. So for each of these terms, I'll calculate the score and add them. That's what this summation is signifying. Like, yeah, that's the most obvious thing to do. And again, it's term frequency multiplied by the IDF. So TF into IDF. But here TF is not just the frequency. It is frequency multiplied by k1 plus 1 divided by frequency plus k1 into. Okay, so what is this happening is, I just want to scale that frequency such that it does not uh, get biased towards longer documents. So this mod D is the length of document, and average DL is the average document length that is there. So this mod D upon average document length is a measure of how long my document is compared to others. And this K1 and B are just hyperparameters which I can control. So yeah, if my document is of the average length only, then you can see the B and B will get cancelled. It will actually have no effect. But if my document has it is longer than usual, then my denominator will become larger and the score will reduce, which is exactly what I wanted. And yeah, the IDF is also not the same. Instead of having uh, in TF-IDF, we actually had capital N upon NT. Capital N is number of documents upon number of documents containing term T. Here we have N minus NT. Why N minus NT? Instead of having the total number of documents, I am taking the fraction of number of documents not having the term T divided by the number of documents having the term T. And this 0.5 both places is just to ensure that those terms don't become zero. Like yeah, I could add an epsilon also with some 10 power minus 6 or something, but that will still have a very large value. Like, I don't want steepness, I want a smoothness. So I'm just adding 0.5 both up in the numerator and denominator also. And again, I'm taking a log. Yeah, instead of log, I can actually take any concave function, say a square root or anything which smoothens the function for higher values. So yeah, but here we use log, and log actually gives the best performance compared to all other concave functions. So yeah, log is what is used. Yeah. Any doubt till here?
Uh, Akshan, the code for TF-IDF.
Sorry.
You wanted to share some code in between.
Yeah, I wanted to, but now I think like whenever I'm trying to share my screen, my laptop is lagging. So I'll show that later. Is that fine? Yeah,
Yeah,
like
yeah,
I
okay.
wanted to show that code like just for term frequency. After that, I do it for TF IDF and for BM25 also, and both give reasonably good scores for the correct terms. So yeah, I'll show that later. For now, I think we can move on.
Yes. Yes.
Yeah. Okay. So till now we were just considering words as words, like words are words. What else are words? But now we will start with the thought that words can also be represented as numbers, because a computer likes numbers, AI likes numbers. Like everything in AI is everything in ML is just matrix multiplication. So we want words represented as vectors. So yeah. So before that, okay, so we have a vocabulary which which is not exactly the way we think of vocabulary. We think of vocabulary as a dictionary of words, like I have words. For the computer it may not be necessarily words but parts of words, maybe. Suppose I give a word, I say take the word computer. The computer can be broken as compute and like, because even if we see in somewhere in our brains, computer is more associated with the word compute. Like the verb compute tells that okay, the computer does some computations, it does some calculations and all. So that's how we want to we understand it, and that's how we want the model to also understand it. So yeah, as you can see in this example over there, today is a beautiful day outside is broken in some way. So yeah, so this process of breaking a words, first of all, is called tokenization. So there are two main kinds of tokenizers. Yeah, sure. Can you go to the next slide? Yeah. So there are two main kinds of tokenizers. Like I have a sentence, I want to break it into tokens. Okay, I'll not call it words now. I'll call it tokens. So I can either go with word tokenization. Word tokenization is just what I told you just now. Take words as it is. Like in this case, suppose I take this sentence: grouping happens until set vocabulary. This will be broken as grouping happens until set, like each until I reach a space or a full stop or any punctuation mark. I just take that entire thing as a single word, as a single token. And there is another thing called byte pair encoding. So what is byte pair encoding is, we start with all, okay, first with word tokenization. uh, the number of the vocabulary depends on the data. Like suppose my data does not have a word, it will not appear in the vocabulary also on the training data used for tokenization. And rare words will remain as individual units. OOV words are nothing but out of vocabulary words. Like, so I suppose I have made a tokenization of a training data set, and suddenly I am giving it a new word, say a proper noun or something, like suddenly a new word. The model cannot do anything because it has not learned that word only, and it cannot represent it in any ways. So, and it is also heavily language dependent. Like, it depends on what language I took, what data set I took from. So word tokenization is not preferred mostly. What we prefer is byte pair encoding. So byte pair encoding is it starts with all the ASCII characters as tokens. Like for now, consider the ASCII characters as alphabets. So from A to Z, all of these individual letters are tokens. Okay, so using only these tokens, I can write anything I want. Like any sentence can be broken into letters. So that's what I'm doing. But what I'm doing is, I know that if I just take letters as my tokens, it will not be very effective. Like, what meaning does T have? It has no meaning. But if I write a combination of letters, say TOKEN, and I get a word token, token has a meaning. So I don't want letters only. I want some groups of letters also. So iteratively, I'll merge tokens. depending on their frequency in my training data. So I see that in my training data, E and R occur together very much. Like is a very common word. So I'll create that as a new token. Like I'm just developing my vocabulary. So how will I develop that? I'll develop it in this way. I'll take ER as a word in my token, a token in my vocabulary. Similarly, all the commonly occurring two-letter words. Now again, words that can be made, tokens that can be made by combining these single letter and double letter words will also be added to our vocabulary if they are frequent enough. And like this way we can see that vocabulary size in our control. If if we want to stop after the three letter merges, we can stop it just at that time, and still we can represent anything, any sentence in terms of our tokens. So this is important because it has inbuilt OOV handling. OOV is again out of vocabulary words. Like suppose I gave it a new word, it can always break it down, even if the entire word is not in its vocabulary. So that is an advantage. And yeah, it learns from a global corpus. Yeah, it is not learn tokens only from the training data. It can represent even out of training data words. So yeah, any doubts still here? Yeah, okay. So now coming to our main motive, I want to represent each of these tokens as a vectors. So that I'll call as a embedding. So embedding is a dense fixed size vector representation of a token. Again, dense and fixed size. Fixed size because obviously I don't want one vector to be in one word to be in some embedding, some vector space and another to be in some another. So I want to represent all of those in a single vector space. So I want it to be fixed size, and again it should be dense. It should not be sparse. Like okay, I'll come to sparse later. Okay, and what these vectors the properties that these vectors should have is that their meaning should be easily interpretable by the model. Like even though if we couldn't interpret, the model should be able to interpret their meaning. Uh, what I mean by that is if there is a vector which is say king, like the vector associated with the token king, and there is a vector associated with the token queen, they should be at least nearby each other, and the vectors, other vectors near them in the vector space should be something like royal, prince, princess, like things like that. Similar words should be grouped similarly. Uh, I should I sh like there is a TensorFlow projector. Uh, I think I'll try sharing my screen now. Yeah, I think Viveka people might be familiar with this. So this is basically a PCA projection into three dimensions of these embeddings, which are learned previously this word to vec technique. And yeah, in this I can you if you see all these blue dots are actually words. Yeah, and over here we are using a word tokenizer and not a byte pair encoding method, uh, just so that we can understand its meaning. So yeah, if say I like we can just see that similar words are grouped similarly. Like if I search for the word intelligence, I'll we can isolate the nearest 100 points and see them. Is my screen visible? Yeah, it's visible. Yeah. Okay, so we can see all the words similar to intelligence are represented over here. Like all the words semantically similar, like their meaning is similar to intelligence, are also represented in this data. Yeah, wait. Yeah, so what happened? Yeah. So you can see actually intelligence has multiple meanings. It can also mean wisdom, psychology, things like that. So all those things are over here. There can be artificial intelligence, so artificial intelligence, AI, lab, things like that are over here. And intelligence can also mean the security level intelligence like agent, spy, officer, things like that are also available here. Now, when it comes to commanders and like things like that, there is also this things associated with the national security, alleged powers, actions, things like that. So, okay, so what my point is, if even if a word has multiple meanings, the words semantically similar to it in multiple ways will be shown by this data. So, yeah, and yeah, Sharan, can you continue sharing your screen now?
Yeah, sure.
So this is what I want, and now we'll get to how do we achieve this embeddings.
It's visible, right?
Wait, it's not visible to me. Yeah, I'll not try sharing my screen now.
Uh, is it visible to others?
Yeah, I think screen is visible. Uh,
Okay, yeah. So this is what I want. Like the semantically similar words should be near each other, and actually, okay, yeah, that's what I want. You can go to the next slide, Sharon. Yeah, so if we want, we can actually directly use one hot encoding. Like one hot encoding is like associating a dimension to each word, and just like you can see, Rome is given 1000, Paris is given 01000, like things like that. So we can just have a vector representation. But the problem with this is it is the simplest, and that's the problem. Firstly, it is a sparse. The the things most of the things are zero. You cannot expect to do some math with this. Like any math related to this will be trivial. Then there is no notion of similarity. You cannot say that Rome, Paris, Italy, France are all countries, so they will appear similarly. There is no generalization because again you cannot learn anything. You cannot improve this. And again, it's too large. My embedding dimension will be the size of vocabulary. So that is not what I want. So there are two main ways how embeddings can be learned. One is by matrix factorization. Like I can have some co-occurrence matrix. I can basically I can use statistics to find a good vector representation. And another is shallow depth window, which I'll explain in the next slides. Yeah, Shadan, you can go. So yeah, what this works, the principle on which this works is this is called the word to vec technique, word to vector, and it was first proposed in 2013. So how this works is I'll break my entire vocabulary into tokens, entire sentence into tokens, and I'll convert it to one hot encoding. Now, I'll have a learnable embedding matrix. Like I'll have kind of a lookup table for my vocabulary. So the lookup table will have dimensions of D cross V, where V is the vocabulary size and D is my the dimension of each vector that I want. Now what I'll do is there are two methods. One is CBOW, which is continuous bag of words. Another is scriptgram. What I'll do mainly is in CBOW method, I'll take some context words, like I'll take two words before and two words after, and I'll try to predict the central words vector representation. Like I'm taking input as the vector represent embeddings of the previous and later words, and I'm trying to predict the trying to predict uh, the most probable word that should come in the center. Like I am trying fill in the blanks. And skip gram is I'll have the central word and I'll try to predict the other words. Okay, so can you go next, Sharan? Okay, so the basically the architecture of CBOW is I have suppose I had the sentence as to the guy who invented. I'll take the embeddings of to, the, who, and invented. When I'm multiplying it by WE, I'm actually taking their I'm using the lookup table to find their embedding. I'm adding them. I'll average them, like add and divide by 4. And this vector, I'll train a neural network to predict a distribution, a probability distribution on all the words on what can be the central word. So what I'm basically doing is it's an unsupervised learning method. I don't need label data. Like the labels can be generated on spot in the data itself. And what I'll try to do is this the linear layer that you see over here, FCN, has input as a d-dimensional vector, where d is the dimensionality of my embedding, and the output is a v-dimensional vector. V is the size of vocabulary. So what I want is I am this the output of this v-dimensional can be converted to probability using softmax, and I can use this softmax to now if I have softmax, I can take loss as cross entropy loss, and I can use backpropagation to train the weights, and I can update the values of these the vectors, the vector embeddings of these input words like to, the, who, and invented. So it is called a continuous bag of words. First, continuous because my values are going to be continuous, like they are not going to be binary or something. They are going to take continuous values in real numbers. And bag of words because again I'm considering it as a bag of words. It does not matter if I say I am going to Delhi or Delhi is going to I. Like I'm just taking the average of the embeddings of all these tokens. So I'm not actually considering their order. So that's why it's a bag of words. But anyways, we don't even want their order. We just want to learn good embeddings. And the generated embeddings are an average. Yeah. So yeah, if I have vast training data, this I can hope for this training process to finally converge to a better representation of all my words. So yeah, this was about CBOW. Any doubts still here? Okay, fine. So the next technique is skip gram. So skipgram is like just the opposite of CBOW. In CBOW, you had the neighboring words and you tried to predict the central word using them. Here we have the central word itself, and I'll try to predict the neighboring skipgram again. Okay, so the word is skipgram. If you see n-gram meant a collection of n words in order. So skipgram means a collection of words where some middle words are missing. Like I have the central word and I am trying to predict the third word after this without having the context of what are the two words between this. So that is what I'm trying to do over here. So taking the sentence again, to the guy who invented. Now I'll take only the word guy and I'll try to predict the first word. I'll try to predict the second word. I'll try to predict the fourth and the fifth word using this central word. So again, the training part is same. The input is going to be my d-dimensional vector, which is the dimensionality of my embedding, and my output is going to be v-dimensional for each of the word. Like for each of the positions, I'll predict a distribution, and using that again I get a softmax function, so I can use cross entropy loss to back propagate and train my model. Yeah, so any doubts in this architecture?
Shall I have the code open if you want me to share that?
Sorry.
The code, would you want me to share it? I have it open.
Yeah, if you have it open, then yeah, do share it. Like I wanted to, but whenever I'm trying to share, it's like
No problem.
lagging.
I'll share.
Yeah, you can explain it.
No,
Like
go
you will
ahead.
have a better idea.
Would you like to explain or shall I go ahead?
Yeah, you explain it. Like you can explain it better than me.
Okay, so the idea of CBOW was to produce the embedding vectors that we get in the end. And see, the two things are important here. One is that words can be similar, and two is that their similarity can be manifold. Like if you see, some people would really say cats and dogs are like opposites. But if you see, in some sense, both are animals, so both are similar. So the reason why we have a high dimensional embedding space is because we can capture these multifold similarities because of the vast dimension, because of the dense vector, like so many dimensions. So here we try to recreate the CBOW approach and train a model so that we get the output embeddings. Now, see, we want to be able to do some vector algebra with them, right? So because then it helps the model learn easier when, see, this is not our final aim. After that, you're going to train some text model on it and make it predict maybe. So you want that model to, let's say, you want this to help the model learn rather than the model learn a way around the embeddings. So vector algebra is important for that, and because of that, you can say things like king minus man plus woman, which is basically subtracting the male gender from the king vector and then adding the female gender, should produce everything identical except for it should end up with a queen, right? So that's our final aim. So if we take the cosine similarity of all the words in the vocabulary with the vector that we end up with when we do king minus man plus woman, we should end up with queen as the top one. That's our aim here. So let's start. I'm not going to go through line by line, but I'll explain basically what it does. So we take the IMDb movie reviews dataset, so 50K movie reviews. And here I'm using NLTK, so which is Natural Language Toolkit word tokenizer, right? So no byte pattern encoding. And yeah, so these are, so you have 50,000 reviews basically. And see, some of these reviews will be having some things like HTML tags and abbreviations. since you'd want your model to learn better, you would want all those to be either removed or merged into one representation, because having many representations for the same thing is only going to reduce the frequency that you have for each. So after cleaning, it looks something like this, which is basically only words, no HTML tags and all. And then, yeah, you basically tokenize. After tokenizing, this is just one review. You end up with words, as you see. Right. So let's, yeah. So then we create a vocabulary. So that is easily done. Just pass through all the tokens that you have, and anything that's not there, index and add. Right. So after you do this, you see, this is important. If see, in CBOW, you have context words and you're predicting the middle word. So when you're doing that, you let's say a word has only occurred once or twice in the whole vocabulary in all the 50,000 reviews. Then how much do you think the efficiency of what the context word learns, what the target word learns from the context words, or what embedding is learned for that word which occurs 1 or 2 times itself is going to be? Not much, right? So it's not that useful. So initially the vocabulary size was some 46,000, and then we basically we define a minimum frequency. That is, if here it's 55, that is, if a particular word occurs less than 55 times, just remove the word and replace it with an unknown token, which is better because it helps it helps keep that representation uniform in the sense that you don't have 10 different vectors for words which occurred once. It's just one unknown vector, and removing it won't be of any use either, because the sentence is going to lose some meaning, right? So now you have a decently sized vocabulary of 10,600. You guys can hear me, right?
Yes.
Yeah, you're audible.
So then you basically encode, and so after encoding, you would see that these are the indices for the vocabulary. So it starts with exclamation mark, comma, keeps going, right? So sorry for the long output, right? So yeah, right. So here it's important to choose an optimal context size. Context size in my case is defined to be how many words on the left side you want to take, or how many words on the right side you want to take. So totally, I'm taking 12 words as a context of predicting one word. So yeah, then you create a data set, and yeah, so then you just have you have your embeddings. You have an embedding layer, and Pakshal will come to that in something in the next slide, that the embedding layers here, what I've used, do not have a bias term. So Torch doesn't give a bias term for embedding layers. You can add it if you want. Will turn out to be pretty interesting. And yeah, so then you have a feed forward layer, which basically gives you logics over the whole vocabulary. Choosing an embedding dimension is equally important, because your embedding dimension basically gives you more ability to learn stuff. But if you don't have enough words for it, then it's going to be sparse, right? So then basically you train your model, and then see, when you train embedding models like this, you can save them as meta and vec TSV files and put them in TensorFlow projector to check how your embeddings are. So if you want to train, you can do that as well. Yeah, so this was our aim, right? Our aim was basically to test king minus man plus woman. If it ends up producing something that is closest to queen, right, then we've done a good job at our embeddings, because vector arithmetic is working out, and that is what is happening here. God forbid why Hong comes next. God knows. But yes, so you already so you see some you see the one that we want is on top. Then you see some things that maybe if you see the reviews, you can explain why these are coming up, and then you start to see some things that are actually useful again as well. So Elizabeth is a queen, so she's probably popped up a lot of times in the context of queen. Princess, yeah, queen and princess. I mean, you get the point, right? So, and another thing is, so we try to find analogy of is, was and were. So if you do is minus was plus were, what do you get? You get are, and that makes sense. And some of these make sense as well if you think about them carefully. But given that you see, if two words occur in the exact same context, they're gonna have embeddings that lie close to each other or are similar, right? So this makes sense because if you say something exists, it seems to exist. All those come in the same context. That is why including it, seems to exist. All these words also come up here. So that's basically it. I think Pakshal will continue. If you have any doubts, you can ask. Pakshal?
Yeah, okay. So, okay. So one thing, whenever otherwise we train a neural network, we have a bias term. So do we take a bias term here or not? So that's a question. So the thing is, first of all, we are not having any activation between the while taking the emitting from the emitting layer and averaging it and sending it to the final output layer. We are not having any activation between that. So even if you remember the DC app last year had a question similar to this, the thing is the bias of even if the bias is there in the embedding layer term or in the output layer term, it will finally result as a output bias only, and vice versa also. So what is happening is, suppose I have my embeddings, and if I shift them by a bias vector, say some vector, it won't actually change the spacing of those vectors. It won't change how similar they are, how what is their neighborhood and all. It will just be like translating them in their vector space. So bias likewise does not has any direct relevance in this training process. And actually also in the original papers also they did not take bias, because it theoretically it should not matter. And even in the final paper, even in while training, they tried training using bias and without bias, but it did not give any change in accuracy. So yeah, biases are like for CBOW, you can have a bias and it will still result as a output bias only. Yeah. Sharat, can you go to the next one? Yeah, so okay, so now, till now we did not talk about computational complexity, like how much time will it take to compute things and all. But yeah, this time if we just look at it, whenever we are predicting, even in CBOW or skip-gram models, we are actually predicting a distribution over the entire vocabulary, and then we are trying to use the back propagation and all. So first of all, to predict that entire distribution, we need a softmax function. And a softmax function, if you know, it is of the form e to the power a. Like say I have w1 w yeah like suppose my output positions are w1 w2 w3 till wv. My softmax at each position will be e to the power wv divided by summation of all e power wi for all my uh, positions. So that is going to take a lot of time to calculate. So one trick to get faster inference is using Huffman tree, and it introduces something called the hierarchical softmax. So what this does is, I'll once I have the vocabulary, I'll spend some time to create a tree out of it. So this tree will be such that the common words are on the top and the rare words are at the bottom. And I know where each word is there. So now suppose my correct word is say a wood. And okay, huh, and also to the to each edge I'll assign a probability. So if this is my say this this n4 comma 2 has these two tokens backslash s and n4 comma 3, I'll assign a probability to each of this edge, and that will be that will be what I'm trying to predict by the model. So what I'll try to do is, suppose I my predicted my central word, yeah, in a CBOW architecture, my central word is wood. What I'll do is I'll just calculate the probability you are using coming from here to here, and the probability of any leaf can be calculated as the product of the probabilities of each of the part on the edge. The probability of good will be the probability mentioned on this edge multiplied by this one multiplied by this uh, okay, you are not able to see my cursor. Yeah, it will be the probability of uh, the ones of the product of the probabilities appearing on each edge on the path. And the advantage of this is I don't have to calculate the probabilities of the entire tree if I want to take a softmax. Like I know the other things are going to be just a product of this, so I can reduce my complexity to just big O of log v instead of big O of v. Yeah, was I clear about this? Okay, then Sharan will continue with Gloway methods.
Yeah, so we'll pause for doubts here. If anyone has any doubts, you can ask Pakshal, and then we'll continue, and we'll go a little bit faster because uh, like time is running out. So any doubts? Take that as a no. So the second type of methods, other than shallow window based methods, were matrix factorization methods. And matrix factorization methods basically factorize the word co-occurrence matrix, which is in the context of any given word, what are the counts in the whole corpus that some other word occurs, right? So while SIBO tries to ask the question, given the surrounding words, can I predict the middle word correctly? So it's a predictive method. Glove is technically in a bit of matrix factorization as well as the predictiveness that SIBO has. So what it does is it tries to ask this question: if two words appear near each other in the corpus, then their vectors should be similar. Uh, as you can see, straight off the bat, this might not make much sense, just like SIBO. But if you think about it, that is how our language is processed also. So it should make sense, right? So what do we do in Glove? So Glove is global vectors for embedding. So first you build the co-occurrence matrix, and this is a one-time thing. So just take the entire corpus, and for each word I take some context window and see what all words are occurring and add the count in this B cross B matrix, right? So after that is the learning space, is the learning time. So what do you learn? Glove learns four things: a vector wi for each word, then w tilde j for each context j, right? So that's two vectors, two weights vectors for the same word, and it also learns two bias terms because biases are important in shifting the space, let's say. So the intuition behind Glove is that, see, if you take these, if you take a word's meaning and you put it together with its context, and you shift the space by adding some bias terms, it should tell you about how frequently that pair is occurring, right? That pair is occurring. So, but like Pakshal explained before for, I think it was TF-IDF, here also you have a log because, I mean, one thing could have occurred 4 times, one thing could have occurred a million times, and you want to keep the scale proper so that learning is better. So yeah, so model learns easier if you normalize using a log. And the loss function here is basically going to be a weighted square error. So the square error is obviously of your prediction, which is wi transpose w tilde j plus bi plus b tilde j minus the actual value that is supposed to be, which is log of the co-occurrence matrix's value for that particular ijth entry, whole square. So you might ask, why is this f of xij there? It's there because, see, let's say you have to comfort one of two people. Okay, a person who is, both of them are important for your business, except one guy comes every day and the other guy comes once in a month. So obviously the money that comes in from the guy that comes every day is going to be more. So you would tend to him first and then try to accommodate the guy who comes once a month. That's what we're doing here as well. Just because um, just because let's say you have some occurrences and you have some occurrences that keep coming up, like all these will co-occur with other words more than other entries of this, like randomize. So you want to give some weight to this and say minimize, give some priority. That's why minimize. That's why you have the weight function, right? So something you might want to know about Glove is that the training is done using the same optimizer you train any neural networks. So you look over every pair I here, so every entry in that matrix, and you calculate loss from gradient descent or any let's say different version of it, and you update the vectors. The initialization embedding vectors are often randomly initialized. So I mean, what will you do? And the thing is, almost often, even in the implementation that I showed you for Zero, that initialized from a uniform distribution. So to prevent, let's say, too much chaos. And so you start random, and there's this idea that the gradients can be used to shape the space to create the embedding, to create the dimensions, that the latent space that you have, right? And what is the final embedding? Is it wi or w tilde j? So most often both are added together because you don't really know if in the sentence it's more useful to use the context part or the thing that it's a subject. So you add them, and is Glove really better? So I told you the first this thing before, that Glove preserves globality because now you use a shallow window, true, but you use that shallow window to check for the entire corpus initially. So you build the co-occurrence matrix once and you can reuse it. That's one thing. And the other thing is that it's also a predictive method. So it's not something like where you, let's say, you so it's something that still predicts an output and you back propagate for it. So it's in both places. And so yeah, I've told you about the symmetry because you never know when it's used for what. And is it the best? So this came out about a year after the CBOW. So it's by no means the best, but it's very good. And one more thing you'll want to know is, see, if you have one-hot vectors like Pakshal mentioned, then you would be actually training your model. Your model would be learning around it. It has to learn a way around to interpret these vectors. It has to put extra effort to learn that these vectors mean these things because they're all orthogonal. But if you have some pre-trained embeddings like Glove or CBOW, then they're helpful in helping the model to learn using them, right? So, but it's not, this doesn't fit all models. So it's a better idea to train the embeddings from scratch as a part of the model. So the embedding there is also optimized like end to end. So you start with one hots and you end up with whatever model you have in the in the back end, and you go through a training process for the whole thing, right? So Pakshal. Pakshal.
Yeah, so just coming back to this, if you remember in the TF-IDF slide, we mentioned that there is an unexpected advantage of TF-IDF. So that is this. If you remember, we had a matrix. Okay, you did not see the TF-IDF matrix, but you saw the term frequency matrix. In TF-IDF, you were just multiplying each column with scalar. So yeah, basically we have a matrix whose columns are the words and whose rows are the documents. So now if you see, if I can take each of these rows, I can isolate it, like I can treat that row as a vector, and I can say that that vector is of this document. Like each vector represents a document. So I will have a v dimensional vector Okay, so V dimensional is not a good size, but yeah, again, that it can be considered as a document embedding. Like I'm embedding an entire document as a vector. And yeah, since it is sparse, it is high dimensional, so it may not be, it also does not capture any context or meaning. But yeah, it still can be considered as a representation of the document. And one advantage is it is interpretable. In these learned embeddings, or whatever was covered till now, CBOW or word to skip gram, you cannot finally say what is the meaning of each dimension in that embedding. But here you can. Here each dimension is a measure of the frequency of that particular term in that document. So yeah, and this document embeddings can be conveniently used for tasks like document clustering or classification. If I want to say classify documents as classify mails as spam or not spam, I can use the document embedding. So yeah, it is kind of like we started with TF-IDF for document retrieval, but it had an unexpected advantage that we can use it as a document embedding also. Yeah, you can continue, Shada.
Yeah, right. So let's go into text generation models. We'll cover three models pretty quickly. So RNNs, LSTMs, and GRUs, right? So why is there even a need for RNNs? So there's two problems. Basically, see, if you have the statement Harshita and Anirudh eat ice cream, right? And let's say I send it into a feed forward network. I convert into embeddings, all that I do, and I send it into a feed forward network. The feed forward network might have some kind of first of all, it will not read the sentences in a sequential manner. So even when you're reading this, you read no and then you read way, right? So models can't, normal artificial neural networks can't do that, reading one token at a time. And there's no way to store the context of what you passed in now. So if you didn't know that the first two words were no way, or if you didn't know the first word was no, then the whole meaning of the sentence is altered. And you have no way to keep track of what the meaning is, right? So these are the two problems. And how do RNNs solve these? So you can see, that's WHY, by the way. So you can see that on the left side is a folded version of a recurrent neuron. So what it does is it takes in this previous hidden state, which you can think of as a summary of whatever has been parsed till now from the time it was 0, right? It's a vector. And it also takes in the next token as the input. So the embedding of the next token. So what it does is it parses through one token at a time, and it projects its previous hidden state using a weights matrix, that is WHH, and it projects its current its next input tokens embedding using a matrix, that is WXH, into and adds a bias term and an activation function to give you the next hidden state. So basically, a summary of what has come till the previous token plus a summary of what's come till now is going to be a summary of what's come plus what's come till now plus what's come now is going to be a summary of what's come till now, right? So that is what this uses. And if you unfold this, you will see that basically is like this is one hidden state transformed to the next hidden state given the next input, and the same thing again and again, right? So how do I'll say the trouble of going through the math. It's there. You can look it up. You can look it. It's there in the next slide itself. But basically, what happens is your inputs flow this way: hidden state input, hidden state input, hidden state input to the next hidden state, right? And you can take an output whenever you want using another projection, which also has to be learned, and a bias term, right? And then you calculate a loss because you know, let's say you're doing next token prediction, right? So you're given a sentence, you pass the first word, your hidden state starts from 0. Then you pass the next word, your hidden state now contains some form of the first word, and now it contains 2 words, 3 words, 4 words. And then this summary you can just project using another matrix. When I say project, I just mean multiply by a weights matrix and then add a bias term, right? And you can you know the next word, so you can take a loss function, cross entropy or something like that, and then the gradients flow back starting from the last time step, right? And then they accumulate with for each time step, they just keep flowing back till you reach the first time step, right? So I'll save you the trouble of going through the math. You can look at it when you get the PPT. Yeah, so it accumulates gradients over time and uses it to update the weights. So often this back propagation through time, or BPTT that is called, is truncated to a fixed number of steps. And you might ask why. When that's coming up, one obvious reason is that see, if you had, let's say, a 10,000 token sentence, right? You would have to go 10,000 steps back. That would take time for one loss that you calculated. So you don't want that. So that's one reason. The other reason is that it's not that efficient as well, because you will see with RNNs that there tends to be this problem of long-term context dependency. So why update the initial weights when why update the weights according to the initial things when they've probably forgotten them at the end? They didn't contribute to it, right? So you can have multi-layer RNNs, and what do they signify? So in a standard RNN, a single layer processes one time step at a time with a single hidden state. So think of multiple layers as a way to allow the model to capture better features. So let's say you had a character RNN, which is not going to predict which is going to predict tokens, but the tokens are not going to be words or even, let's say, things like your normal tokens that are parts of words or words. They're going to be one character, one ASCII character, right? So that is going to be this thing. So if you see, that model struggles more because it first needs to learn. It doesn't have the advantage of already knowing that A and D is a spelling of and. See, your GPT or your normal RNNs, if they're not character based, have the luxury to, if they predict a token, the spelling will be right, right? I mean, doing byte pair encoding will slightly screw that up, but yeah, you'll be fine mostly. Compared to these guys, you have to first predict that A comes and then N comes and then D comes and then a space comes before they can get to the next word, and then again do that for the next word. So the first layer probably is gonna get things like low level features, like let's say spellings, or like let's say that space comes after every word. Things like that also have to be learned, right? So and then if you have higher layers report more rich features, like let's say context of words and things like that. Because only if you have context of what spellings are, then you even make up words to have context of those. So it's like a lower to a higher level feature extraction, you can say. So right. So if you want to take an output, where would you take it from? Would you take it from a place where the model is just learning to group words based on spellings, or would you learn from a place where the model has learned to learn on those spellings? Obviously the latter. So you take it from the highest or the highest hidden state, right? So do you notice something here? So this was not a character RNN actually. This is, I'm coming to this. This is a normal word RNN, right? So word-based tokenization, but still you see problems like these occur. Don't, it's supposed to be don't. I'm not sure how it has an N apostrophe T token, or was it an N and then an apostrophe and then a T, but it wants to say don't, but it doesn't know that the space shouldn't come in between. So things like that are there, right? So yeah, so these models are usually deterministic, which means what? Which means that given a particular hidden state or given a particular input, the output is actually fixed. But then every time you ask GPT, you get a different answer, right? So that is kind of their way of making sure models have creativity and they're not just spitting out either the same word again and again, because that also happens, or they're not just spitting out the same answer to everybody. That's basically seems like some form of hard coding, even though it isn't, right? So there are three things. One is temperature. Temperature scales the logics before softmax. What are logics? Logics are what you apply the softmax on to get probability distributions. So you can say for certain that if something has a higher logic score, then that thing will have a higher probability than the other thing which you compared it with. So lower temperatures often make the model more deterministic, and higher ones make it creative. Sometimes too creative, they start speaking out of topic as well. That's there. And you can see that clearly here. So the exponential function is basically going to curve whatever you scale it by. So it won't be uniform for all of them. That's what I'm saying. So then there's top case sampling, which is like, why take the greedy approach and choose the best probabilistic token when you can go through the top 4 or 5, let's say, because they will be equally good. They will generate different responses, but at least that way you it even helps keep the model on track actually. Okay, so choose from the top k highest probability choices after the softmax. Choose from the top k. Logics will also mean the same thing, but and next thing is nuclear sampling, just top p, which is like, why choose the top 4 or 5? all the time, when you can have that niche case where you're like 0.8 is the first token's probability, then it's not like 0.02, 0.02, 0.02, 0.02, and I gave top 5. It's going to take one of those 0.05, 0.02 tokens more number of times than the first one, right? Why have that? So what you do is you kind of try to eliminate it by saying, you know what, the top n which sum up to point something, which I will decide as a threshold, I will keep, right? So what are the problems with RNNs? They are multifold. So 3 in this case. Hidden state accumulation. So they're very bad at long range dependencies because the number of dimensions in the hidden state are fixed. So asking it, let's say it has taken 56 tokens inside, okay, and 56 tokens has been encoded in the hidden state. Now you give a new 57th token, and it has to encode the 57th token as well, except it's already running out on some sort of, let's say, space or compression. It doesn't have much more space. Then you start leaking out whatever was there at the beginning. So long form context, just there's no news RNN, let's say. So gradient flow is one more problem because we keep multiplying by the same WHH matrix n number of times. It's possible that you end up most of the time with vanishing or exploding gradients, which is another reason why you want to truncate your backpropagation through time. And lack of parallelization. I mean, if you ran an RNN, you would have to run one step before you can run the next time step, and that isn't very efficient when you have these high power GPUs asking for more numbers to crunch, right? So right. So an interesting thing that's been done with RNNs is RNNs with attention. So these are encoder decoder based models. So the encoder in orange actually reads the input as usual and maintains hidden states. It's a normal RNN, right? And then you have your decoder. So what you're going to do is you're going to give you're going to apply attention on all of these, and then you're going to decide which part of each hidden state to focus on, right? And this differs for each decoder state, right? This differs for each decoder state, and this context vector that you get from the attention weighted vector, which is a context vector, we call it. It's a weighted average of hidden states, and it acts as a soft spotlight. So what that means is it helps focus your attention. That's why it's called attention on which token you would, on which embedding you would like, modified embedding, hidden state basically, right? So and then the decoder starts spitting out its it goes through the same RNN procedure and starts spitting out outputs, right? So yeah, that's it, right? So I'll take any doubts here, and I have the code implementation, so I'll share that. Any doubts? Right, so let's see the code. So I have a couple different modifications here. So this is a single layer RNN, but I think it's best we start with a character RNN, right? So this was the one I was talking about, a character RNN. So what is a character RNN? It predicts one character at a time instead of one. So tokens are characters. That's it. So all these models, all the 3 I'm going to show you for RNNs are trained on Robert Frost's collection of poems from Kaggle, right? And you can see my screen, right, guys?
Yeah.
Somewhat. Yeah. Okay, fine. So these are the hyperparameters that you have in your hand. So again, I'm not going to explain every line of code. I'm just going to go through it and show you some interesting things at the end, right, which motivate how they learn, right? So you create a data set, you name a class. I mean, you make a class, and then you have some functions that help generate text. I'll come to this part. So this, by default, I had used torched multinomial. Torched multinomial, what it does is it samples from a multinomial distribution of that of the logics, right, of the software code. So I'll come to that, right, and then you train, and you see initially it starts not making much sense because it's a character RNN, it has to get the spellings also right. By the way, the woods is what I gave it as input. Start generating from the woods, so that will have a proper spelling. So you see basically nothing gets right except somehow you would come up, but right. So you keep training, loss keeps reducing. You can see the loss here, right? Loss keeps reducing, and then you get to some point where you have a good trained model. So I start with the woods. It says dimly dark. he did not number for me menses. It doesn't make much sense, right? And seek the soul in you, whatever. Okay, right? So it doesn't make much sense. Now, see, there's one reason why it may not make much sense, and for that we'll have to go here where I can show you this sequence length. Basically, see, you need some let's say you need some n number of this thing to give you a context in order to predict the next word. So that is going to be 100, right? So and then I ask it to generate for 300 tokens, so 300 characters. These values are high here because each character is just going to be one letter or a space or something, right? So I give it this much. Sorry, I give it this much, right? And then it predicts these. See, even here you can see it has learned that poems have many spaces or many you know lines, right? It's not just English, so it keeps pressing /n very often. /n is a token for it, right? So yeah, so here what I want to do is I want to show you that even though they may be getting one spelling wrong, the meaning that they want to convey is still there somewhere in the hidden state. So yeah, so if you give it this much, right, and you asked it to predict the next letter after this, so I'm basically now saying, don't just give me a letter, give me whatever probability you use to take that letter, and top 10 you give me. So these are the probabilities. So you can see much, muck, all make sense, right? They're all English words. That is why they're on top. So in some sense, you can say the model is learning to understand what spellings are. This is a one-layer character argument, by the way. And yeah, so what I want to show you here is, yeah, so right. So if you give us, see, I just leave it after as, with, all, and, right? And I ask it to, so it's a big paragraph. And then I ask it to give me the next character probabilities. And it starts giving me, you can see vowels. Because apparently they're used more than the others. I still can't make much sense of this. But yeah, so this was what it generates with the multinomial distribution, right? So I commented out the previous line, and it generates this with the multinomial. So it's sampling from this. And so this is with absolutely no sampling. I tell the model all random stuff, you put a seed on it, and then keep it stuck at 42, and don't even give me a sample version in the last part, right? So, and then this is what it generates. Surprisingly, I don't know why, this is what the model is, all the multiple slashes that are there, the model is not giving them anymore, right? So that is one more interesting fact. And I guess we'll go to single layer RNNs now. So single layer RNNs are whatever I showed you now, basically. Here you will see the sequence length is much lesser because they're tokens now. And yep, this is a one layer RNN. I also show you a two layer one. So all the same. Yeah. So train, and then so here you see spellings will never be a problem. Starts off with good spellings because it's going to predict words that already have the spellings intact, right? So since it's Robert's first, I just gave it, I found the gate was left ajar, and then asked it to generate. So as it keeps training, after it finishes training, it generates this. I found the gate was left ajar, close, that you may be in other way, and it keeps going, right? So yeah, so one thing I'd like you to see here is the output. We'll compare this to the two-layer RNN and see if it understands a little bit more of how English works and how poems work. So just keep this in mind. If you want to read it once, I'll wait for half a minute. By the way, till slept is what I've given it. Okay, don't think it's performing very well or something. This is what it's generated. And it's important that whatever seed text you give it, the text that you give it to generate initially is called seed. It's important that that is more than the sequence length that you're taking for training. Otherwise, you'll have to take random vectors, and that will introduce some noise, right? So I'll move on to two-layer RNNs. So what two-layer RNNs do is they use the same architecture, but they help capture more high-level dependencies. Again, same data set. I've kept the same embedding and hidden size, except that there's one more layer here. Everything else is kept same, including number of epochs, though that needn't be the case. Yeah, so I'm saying have at least 40 words basically when you ask it to generate something. So right, same. Yeah, here it's not necessary, but when you test it out, it is pretty. It's a good idea to keep 40 words there at least. So again, spellings are not a problem when it starts. Keeps going, and then right, and then this is what it's able to give out with a two-layer argument, right? So it's still hard to be make some. These spaces are coming with the tokenization, so you may leave them. It's hard to be still. I went by the new. It's still hard to make sense of. But when you give it a little bit of text to work with and not take random vectors, it is going to do much better than what the singular argument. I see the porter, I laugh together, and a child in or rather than send. That part doesn't make sense, but you get the point, right? So I think I'll go back to LSTMs now. If you have any doubts in this implementation, you can ask. I'll take max like 15 or 20 minutes totally for the session time. If you guys are okay with that. Guys. All right, we'll continue. So then there's LSTMs, which is long short-term memory. So how do LSTMs look? This looks a little bit scary, but totally not, because all it's trying to do is it's trying to reduce the problem of modeling long-range dependencies that were there with RNN. So it's basically gating and maintaining two hidden states. So it has three gates, right? Not that two of them are sigmoid and one is tan. And there's one more sigmoid here for the hidden get updated, right? So that the LSTM maintains, and those get updated using the forget input and output. I forget input and the cell state. So yeah, I'm not sure whether the image is in loading. I'll get back to it. I said whatever is there. So I'll send you the math again. You can look through this. Right? Yeah. So I'll go to the implementation of LSTMs. Oh, sorry. Yeah. So here I'm using the same IMDb dataset that I used for the. You guys can see my screen, right? Guys.
Yeah.
Yes.
Yeah, okay. So here I'm using the same IMDb dataset that I used for the CBOW model, right? So, and this is a two-layer LSTM. So you'll, again, I'm not gonna go through the full code. So I'll just show you. Yeah. So initially, when this is a character LSTM, by the way, so spellings may not be very good. So till this is what I've given it, right? Hope you enjoyed as much as I liked it is what I've given it as a seed and asked it to generate. This is just to monitor how the training goes, right? So initially it would start off with some. See, by the way, this is step number 32,000. So it's already been trained a bunch of times before this. So you might see that it's getting spellings right now, and it's even getting some short form context correct. But interestingly, it's not. What is not getting right is the sentiment of the statement. So these are trained on movie reviews. So you would expect that if you had some good movie review, you would want to continue with a good movie review. But you see that is very difficult to do with a character LSTM. I say it was a very good movie. I loved it, and so will you. Hope you enjoyed as much as I liked it. And for some reason, it thinks this is I and starts with this. But if you ignore that and look at it, it says the film is so inspiring. I was so very disappointed in the movie. So it's not very great in modeling the sentiment, right? Yeah, but the sentence might make more sense than what you see with an RNA. That is shown well here, I feel. Right. So yeah. So I'd like to introduce you to temperature here. So you can see this temperature 0.7 is usually a balanced temperature. So it's not too creative, but not too deterministic. They'll keep saying the same word again and again because that happens very often, right? More often than you think. So yeah. So tell me something good. And then it starts generating. You can read. I just leave this here for half a minute and then we'll move to GRUs. Someone say something.
No, continue.
So I'm guessing that's that. I'll move to GRUs. Anyone has any doubt, please ask. So what GRUs do are, think of them as a simplified version of LSTMs. So the LSTMs have two types of hidden states. They have 3 gates. Why so much unnecessary stuff, bro? And just remove some of those gates now. So basically, this makes LSTMs difficult to train because you have to write so many equations. These days, not you, but GPUs have to run on so many of these equations. So can we simplify it? Or is this so how to make a GRU from an LSTM? So take an LSTM, remove the output gate, mix the cell state and hidden state into one hidden state in some sense, and then rename the forget and input gate to the update gate, add a reset gate and serve hot. Right? That's it. That's how you get a GRU from an LSTM. So what you get with this architecture is basically something that is a leaner, faster version of the LSTM. Right? Again, I'll save you the trouble of going through the equations. You can go through it when you get this. Yeah, so before coming to this, I'll go through some things in the implementation of a GRU. Right, so yeah, okay. So I think, yeah, again, this is a character GRU. So has to learn spellings from scratch. And then some things that might seem interesting here maybe. So yeah, I've kept sequence length to be 100, which is basically taking 100 characters and start breaking the next one and keep doing this iteratively over a window. Right? So this is a 1-layer GRU. And I showed you a 2-layer LSTM. Even though the dataset was huge, this is again on the Robert Frost collection. Even though the dataset was huge, you will still see that this does way better than that. You may account that to the dataset, but the model is pretty good and better than an LSTM. So, right, again, exact same things except nn.gru. Again, we've tried the same thing to stop that multinomial distribution and get only the top argument or the deterministic model. Yeah, and you can see the woods is what I start with. Spunted, as far as I'm aware, that's not a word. Teeth the rather. So, yeah, so keeps generating, keeps getting better. After a point understands that you have to put multiple spaces for it to be a poem. So yeah, you keep seeing longer length and lesser width, right? So the woods is close. More they bought of the load and before it did. Now all spellings are right. Even complex things like some punctuations are right, right? And the loss keeps decreasing. So I stop here. And yeah, so basically it's done 5 epochs and it seems good enough, right? So it's even adding those modern poetic vibes, if you will. Yeah, and so now what I want to do is I want to give it that full context instead of giving it just the woods, like I explained. So the frost lay deep on the furrowed ground and blah, blah, blah. And I wanted to generate a pretty balanced continuation of this. And you see, this is what I've given it, right? And straight off the bat, since it's learned of poetry, it starts understanding that you have to add more enters at the end of each line. So you will not see any capital letters here because to reduce the size of the vocabulary, I've lowered everything. right? So that's one thing to note, because poetry new lines usually start with a new a capital letter, right? So you can read this. The reason I wanted to show this is because I wanted to show you what temperature can do um, to the same prompt, right? So you can take a little bit of time to read this. This is pretty balanced. It's supposed to be. And yeah, this is with temperature 0.2. Remember, the lower the temperature, the more deterministic your models. Means that you will have a higher chance of getting the same word again and again. You will also have a higher chance of getting, um, let's say, things that are that it got from the train data, right? So that's also there. And this is the same thing with a high temperature, which is usually for creative outputs. So I spoke of all, I summoned, things like that start coming, right? So yeah, again, this is where I'd like to show you the interns. What I mean, what is getting from the softmax and what is predicting. Because so again here, I have disabled whatever multinomial it was using. So I've set all of torch number everything to a particular random state, so the results are reproducible. And I've gone to make sure that the top this thing is what is predicted, right? So yeah, so I want to see if I give a full stop, right? What is the next character that is predicting? And you see very well that it's either going to be /n, which makes much sense because you stop with a full stop and you either want a space or you want a /n, or I mean, if it's proper punctuation, you would want either of those to occur, and that is happen. And in some cases, you can get this also because who knows who opened the course, right? Yeah, so that is one thing I'd like you to note, that even though sometimes you may not get this because of the sampling, right? If I put top case 4, then I may get a close course. And you may think, why is the close course coming? Because the model hasn't learned enough to, one, it's top case, so it's bound to come. And the model hasn't learned enough to get some other things down here, like another dot maybe. That may make sense, right? So let's look inside for two parts. One is, so if I give it this prompt and then I say, what is the next token? Or give me the probabilities that you have. It's so it's predicting a full stop, which makes so much sense. And the full stop is much more than the others, you can see. So because that is kind of the end of a line, the end of a sentence, sorry. Yeah, and 2-3 more things. So yeah, so here I add a space, right? So you see, all I've done is I've, after brim, just leaving it like that, there was a full stop that was coming as the natural way to end the sentence. But you see that quickly changes when I add a space. So it realizes after space, why would someone add a full stop? So all letters here, right? Either go to the next line or add a hyphen, because that happens after space, or everything else is a letter, right? So that is one thing that I thought would be cool to see, because we just keep dealing with theory. I wanted to show what happens inside. And one more thing is this thing where the model learns that if you open a quotes, you need to close the quotes, right? So when asked about the scenario, comma space, he said, comma space, after the space, naturally, but this is a doc state, like, I mean, a triple quotation mark. So that doesn't count as part of whatever I give it as input. Only this much comes. So after this, what am I supposed to predict? The model has to think. And when it thinks, it gets space as the best option, or /n or /r. /r is carriage return. It makes sense, right? And if I add a space after that, because after space, you technically have the quotation starting, right? And you see sometimes people don't use quotes. So when asked about the scenario, he said, I am blah, 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 could be the next sentence. Or you see that it properly starts the quotes, right? What about if I add the quotes and then I give the model? So immediately all notion of quotes, a slash and all these disappear, right? And then you start to get proper letters and spaces. Spaces make sense again. And a couple more last things. So yeah, he said, I went to get some water, right? If you leave it at I went to get some water and then don't leave, by this is not part of what I've given it inside. That is saying that's where your sentence ends. So I've given it water, right? What is it trying to think as of then off as the next token is either going to be continue the sentence with a space, or put a comma and continue the sentence, or finish the sentence, or quotation is also appearing here. You can see to close the quotes. But the moment I add a full stop, again, slash and space, all these start coming, right? And that is another thing that I like to show you. Yeah, I'm done. Just a couple more things. So none of the three methods that were shown now lead to parallelization. So you need to run one time step after the next. So GPUs are not of much help, even though they're of so much help. Like they are not performing their full potential with these guys, is what I'm saying. So what if you didn't have to wait for one word before reading the next? You could read them all at once. You could look at the whole sentence at once, and you could let the model decide what to focus on instead of putting them all inside this one constrained hidden state. That's where transformers enter, and there's just no recurrence. It's just pure parallelized static. So which is a fun if you let me do that. So yeah, some memes.